Okay, so here we have an example of a basic chemical reaction or a chemical equation, both of which are the same thing. So we can call this a chemical equation or a chemical reaction. So in this, we have CH4 on the left plus O2 on the right. And this arrow here means yields or makes or produces some CO2 on the right and some H2O on the right. So you can actually get a lot out of this equation just by looking at it. These two substances on the left are called the reactants because they're the chemicals that are doing the reacting. So chemicals doing the reacting. Oops, if I could spell that'd be good. Doing the reacting. And then on the right, you have your products, which, as the name implies, are the chemicals that are produced. So in this chemical reaction or this chemical equation, the reactants break themselves apart and rearrange themselves to make these products over here. Okay, so if we were to take a deeper look at this, the law of conservation of mass says that atoms are neither created nor destroyed in a chemical reaction. That means whatever atoms were present in the beginning have to be there in the end. You can't magically lose or magically gain atoms during a chemical reaction. So let's go back to that. As these reactants over here rearrange themselves, you can't lose or gain any atoms in the product side. So if we were to count these, on the left we have some carbons, and on the right we have some carbons. On the left we have some hydrogens, on the right we have some hydrogens. And on the left we have some oxygens, and on the right we have some oxygens. So if we were to count our carbons on the left, right here, there's only one. And over on the right side, there's only one. On the left side, you have H4, meaning there are actually 4 hydrogens on the left. And on the right, you have H2, meaning there are only 2 hydrogens on the right. On the left, you have O2, which means there are 2 oxygens. And on the right, you have an oxygen here, plus 2 more oxygens here, meaning there are 3. So you can see that something's wrong. You went from having 4 hydrogens to now only having 2, and from having 2 oxygens to now having 3. You can't magically lose or gain atoms. The law of conservation of mass says they're not destroyed. So we have to do something to this equation in order to get it to where we need it to be, to where each side is the same. Now, an easy but incorrect solution would be do something like this. Say, well, I need 3 oxygens on the right, so let's just change this subscript down here to a 3. That would give you 3 oxygens, but you've changed the reaction. That O2 was just good old oxygen. Now O3 is ozone. That's something completely different. If you did the same over here to water and you said, well, I really need 4 hydrogens, and you just scribbled out this superscript and wrote a 4, that's H4O. That's not even anything real, much less water. So when you're trying to figure out where these atoms went, you're not allowed to adjust the subscripts because that changes the identity of what's being produced or reacted. Instead, your only option is to balance this using coefficients out front of any of these chemicals. So for example, my carbons are good. They're balanced, 1 and 1. But these hydrogens, I have 4 hydrogens that go in on the left and only 2 come out. The only way to balance this is to put what's called a coefficient in front of this water, a coefficient of 2. What this means is now, instead of producing just 1 molecule of H2O, you're producing 2 molecules of H2O. And if you have 2 H2Os, that's a total of 4 hydrogens. So now our hydrogens are balanced. But by putting that coefficient of 2 in front of the water, that also means, since you now have 2 H2Os, you have 2 oxygens right here. That 2 carries through the whole thing, just like the distributive property in math. So there are 2 oxygens now in the water, plus these 2 oxygens here in the CO2. So 2 plus 2 is 4. You now have 4 oxygens on the right. So let's go to the left side. Everything is good, everything is balanced, except for this oxygen. You have 2 oxygens on the left and 4 on the right, but if you were to put a coefficient of 2 in front of this O2, again that's 2 O2, so that's 4 oxygens, that will get you balanced. So now that everything is equal, 1 carbon went in, 1 carbon came out. 4 hydrogens went in, 4 came out. 4 oxygens went in, 4 oxygens came out. We have what is called a balanced chemical equation. And balanced chemical equations are produced by using coefficients to make sure that the same number of atoms that go into a reaction equals the same number that comes out. So let's try another. We've got H2 plus O2 to make H2O. On the left we have hydrogens. On the left we have hydrogens. On the right we have hydrogens. On the left we have oxygens. And on the right we have oxygens. On the left you've got 2 H's. On the right you've got 2 H's. On the left you've got 2 O's. On the right you've only got 1 O. You need twice as many oxygens on the right side, and the only way to accomplish that again is with a coefficient of 2 out front. I'm sorry, I wrote there were 2 oxygens there, there's only 1. But now with this coefficient of 2 out front, this 2 applies to these hydrogens and these oxygens. So yes, this 2 does give you 2 oxygens, which is good, but this 2 also gives you 2 times 2, or 4 hydrogens. So these oxygens are balanced, but now these hydrogens are not. We have 4 hydrogens on the right, so the only way to get 4 on the left would be to put a coefficient of 2 out front here. 2 groups of 2 hydrogens is 4, and now everything is balanced. So here's another one. This one involves a polyatomic ion. Right here you have OH and OH on the other side as well. If a polyatomic ion can be found on both sides of the equation, don't break it apart when you're counting it. Just count it as a thing itself. So for example, on the left we have magnesium, and there's 1 of them. On the right we have magnesium. There's also 1 of them. On the left we have chlorine, and there are 2 of them. On the right we have chlorine, just 1 of them. On the left there's a sodium. On the right there's just 1 sodium. And again, since this OH is 1 polyatomic ion and it can be found on the other side, let's not break it up. Let's just count it as hydroxides. On the left you have 1 hydroxide. On the right you have 2. So it doesn't really matter where you start, but start with something that's not balanced. I'm going to start with these chlorines. On the left I have 2 chlorines. In order to have 2 on the right, I'll need to put a coefficient of 2 out front here. That'll give me 2 of each of these though. So I'll have 2 sodiums and 2 chlorines now. 2 sodiums and 2 chlorines. That balances my chlorines. So now I'm going to recommend that you fix whatever you just messed up. We just messed up our sodiums being balanced. Now there are 2 sodiums on the right. In order to make there be 2 on the left, we'll put a coefficient of 2 out here. That'll give you 2 sodiums, but that will also give you 2 hydroxides, and now you can see the equation is balanced. And you know it's balanced once you have an equal number of every atom going in as you do coming out. Alright, on this one's a bit longer. On the left we've got some hydrogens, and there's just 1 of them. On the right we've got some hydrogens, and there's 2 of them. On the left we've got some chlorines here, so it's just 1. And on the right you've got chlorines, there's 2. And then one more, C6H14 reacts with O2 to make CO2 and water. On the left we've got carbons, and there are 6. On the right there are carbons, so there's only 1. On the left we have hydrogens, 14 of them. And on the right there's only 2. On the left there are oxygens, 2 of them. And on the right, there are oxygens here, 2 of them, plus 1 more of them here, so there are 3. So my advice here would be, it doesn't matter where you start with, but generally it's best if there's an element by itself to leave that one for last to balance. So this O2 that's sitting all by itself with no other elements attached to it, I would balance oxygen last because of that. So let's just start with these carbons. There are 6 on the left, so there need to be 6 on the right, so I'll put a coefficient of 6 out front here. That'll give me 6 oxygens. For the hydrogens, there are 14 on the left, so I'll have to put a 7 here because 7 times 2 is 14. But by adding these coefficients, I have completely messed up my oxygens. On the right, 6 groups of 2 oxygens is 12. So that's 12 oxygens plus 7 oxygens here. So 12 plus 7, I now have 19 oxygens on the right. Now you might notice I'm going to have to put some coefficient here to make there be 19 oxygens. But since these oxygens come in sets of 2, there's no number that I can put there that will make there be 19 oxygens. So what you have to do in a case like this is to double the coefficients that you've already placed. So instead of this being a 6, this will now be a 12. Instead of this being a 7, this will now be a 14. So let's go through and count our elements again. 12 carbons, 14 groups of 2 hydrogens, so that's 14 times 2 is 28. Let's get us some little space here and we'll count the oxygens. Oops, I didn't mean to erase my 12. 12 groups of 2 oxygens is 24 oxygens, plus 14 more oxygens, so that's a total of 38 oxygens. Now nothing is balanced, but on the left we have 6 carbons, on the right we have 12, so we can just put a 2 out front here. That'll give us 12 carbons. 2 times these 14 hydrogens is 28 hydrogens. Notice now the carbons and the hydrogens are balanced. The only thing that's not balanced, again, are these oxygens. I need 38 oxygens because there's 38 on the right. So what times 2 is going to give me 38? And the answer there would be 19. So the coefficients for this equation being balanced are quite large, but they would be 2 C6H14 plus 19 O2 make 6 CO2s and 14 waters.